Okay, so we're live on Facebook. Let's imagine these, and so well, I guess we can start. Well, welcome back to one of this Spanish-speaking Acousticians in the Americas events from the regional subject. We'll do a short introduction in Spanish, and then the talk will be presented in English for everybody. Please use the Q&A for questions or the chat to share any comments. Bueno, este webinar va a ser presentado en inglés. En la parte de abajo de la pantalla de Zoom pueden escoger el canal de traducción simultánea al español. El audio original va a bajar el volumen, va a bajar su volumen y se puede escoger apagarlo por completo. Por favor, usen la sección de Q&A que está acá para hacer preguntas y el chat para sus comentarios. Vamos a hablar un poquito de nuestro capítulo regional, el Spanish Speaking Acousticians de Americas. Un poco la misión de este capítulo es congregar y conectar tanto a los profesionales como a estudiantes de la acústica y del sonido en el área geográfica que ocupa Latinoamérica en general, mayormente. Y la función del capítulo es funcionar como nexo entre la institución madre, que es la Acoustical Society of America, y los hispanoparlantes interesados en la acústica y el sonido. Y nosotros lo que hacemos es divulgar y difundir eventos y actividades que tienen que ver con esto y que pueden ser de interés para nuestros miembros. Para hacerse miembro del capítulo no hace falta pagar nada, simplemente hay que entrar en la página web. Si alguien lo voy a poner en el chat para que lo vean, porque no está en esta presentación, y simplemente hacer clic en Únete y a partir de ahí pueden tener obtener nuestras novedades y los eventos que se van sucediendo. Ahora, en los próximos días vamos a tener varios eventos que tienen que ver un poco con nuestra participación en la conferencia del Audio Engineering Society en Colombia, que va a ocurrir ahora en septiembre. Y el 13 de septiembre, a las 4 de la tarde, hora Bogotá, Lima y Quito, vamos a tener un evento muy interesante que se llama Tour de Salas de Conciertos Latinoamericanas, donde varios consultores de Latinoamérica van a mostrar su trabajo en distintas salas, ya sea para su construcción y diseño o para su renovación, salas de concierto de toda Latinoamérica. El 16 de septiembre a las 11:30 am en hora Bogotá, Lima, Quito, también en la misma conferencia AES, vamos a tener un panel sobre auralizaciones. Para los que no saben, auralizaciones es recrear un soundfield, un campo sonoro a través de un modelo computacional. Así que distintos especialistas van a hablar sobre los avances en esta tecnología. Y por último, el 17 de septiembre a las 5:15, hora Bogotá, Lima, Quito, también en la misma conferencia lo vamos a tener al doctor Matthew Neal, que también es de Penn State, que nos va a contar sobre su trabajo doctoral, su postdoctoral en la Universidad de Louisville. Va a hablar de cómo se pueden, con una técnica que él está desarrollando, cómo se pueden renderizar arreglos de parlantes, sistemas de arreglo de parlantes para la escucha binaural. Así que esas son un poco las novedades. Esta es un poco la junta directiva de nuestro capítulo. Yo soy el chair y tenemos un tesorero que es Zachary Littlen, un vice-chair que es Felipe Reinman, una secretaria que se llama Mariana Botero, y tenemos a unos members at large, Andrés Millán y Juan Francisco Mayorga Jaramillo, que se ocupa un poco de las redes y de Facebook para nosotros. Y tenemos un representative national, que es la que nos representa estando en Estados Unidos frente a la Acoustical Society, que es la doctora Ana Jaramillo. También queremos agradecer a nuestros auspiciantes por sus generosas donaciones que nos permiten hacer estos eventos. Así que muchas gracias a ellos. Disculpen un segundo que me voy a pasar yo al canal inglés para no escuchar la traducción. Pero bueno, ahora voy a pasar al inglés nuevamente. So it's a pleasure for me to introduce to you Dr. Cameron McCormick. Cameron is a personal friend from Penn State. And I will give a little bit of introduction on his background. Well, Cameron obtained a Bachelor of Science in Physics from Loyola University in the US. And then he went to Britain to the Institute of Sound and Vibration at the University of Southampton to obtain a Master of Science in Sound and Vibration. Probably there he got into the habit of taking tea at 5 o'clock, which he usually did at Penn State. So then he went into Penn State to obtain his PhD in acoustics. We took together the candidacy exam back in 2017, I think, which is a very comprehensive exam on the basics of linear acoustics, and we passed it. And today Cameron is giving us a presentation on this intriguing technique called acoustic black holes, which can improve, can create vibration reduction in structures. And he has studied the optimization of acoustic black holes for vibration reduction in structures and well, in different systems. So I will stop sharing the screen, and without further ado, I will let Cameron begin his talk. Thank you very much.
All right, thank you, Fernando. Let me get this up here on the screen. Excellent. All right, buenas tardes. Gracias por invitarme. And thankfully, we have TJ to translate, because that's, as awful as it is, that's to a large extent the Spanish that I can speak, unfortunately. As Fernando said, I have been researching for the past few years the acoustic black hole effect and acoustic black holes for vibration reduction. And in particular, I'm going to be talking about some of my work that I've done on structural optimization of acoustic black holes. And I will also be giving an overview of what acoustic black holes are, a little bit of the history, and some of the current research going on. For some of the historical background, I'm going to be drawing a lot from these two sources. I believe they are both open access, but I'm almost certain the second one is, if the first one is not. I'll also bring these references back up at the end in case you don't get all the information down right now. The structure of the talk is as follows. We'll have some background information on what acoustic black holes are, some of the history, some of the current research. Then I'll present an optimization study that I performed in the course of my thesis work on structural optimization of acoustic black holes, and then I'll just have a few concluding remarks. So to start with the background now, first off, it's important to clear up some nomenclature. When we talk about acoustic black holes, there are different meanings depending on whether you are in the field of physics or in the field of engineering. In physics, acoustic black holes were first, or the idea was first proposed by William Unruh in 1981. It's based, it's useful as a black hole analog. It's something that we can create in a lab and measure, and by using some acoustic analogs to space-time, we can glean useful results, useful observations. It's based on the idea of supersonic fluid flow. So you get the fluid to flow above the speed of sound, and then it acts as a black hole because the sound cannot escape that supersonic flow. And an example might be phonons. So as opposed to photons in optical black holes, we have phonons in the fluid, and oftentimes it's a quantum fluid like a Bose-Einstein condensate. In the field of engineering, acoustic black holes, or the idea of acoustic black holes, was first proposed by Mikhail Mironov in 1988. It's useful for vibration reduction, and it's based on the idea of a decreasing wave speed in a thin beam or in a thin plate. Some examples, for example, in a plate might be if we have some dimples in the plate, and it's a means of modifying the structure to get useful vibration properties out of it. Obviously, we're going to be focusing on the latter. meaning of acoustic black hole, and so that's what we'll be discussing going forward. I probably don't need to tell anyone here that there exists a need for lightweight but also quiet structures. It's a classical problem where we want lightweight structures that are also stiff, but that makes them effective radiators of sound. Here I have some airplanes pictured. You can also imagine that in addition to sound, we want to reduce vibration because increased vibration will wear on components and shorten their lifespan, and this is something that we want to avoid. A common solution to reducing vibration in these thin and stiff structures is to apply some sort of damping material to it, but this damping material then leads to an increase in weight, which again is suboptimal for the consideration that we want to keep it as lightweight as possible. And so-called acoustic black holes have or promise a potential for significant vibration reduction, but often will lead to a net reduction in overall weight. I'm going to review some of the mathematics behind ABH theory. I'm going to try to minimize the mathematics in this presentation, but I think it's useful to understand where this phenomenon comes from. It also traces back to a seminal paper by Mikhail Mironov in Russia. This is a scan of it. This is obviously in English. The original was in Russian, and it's not much longer than what you see here. It's just over a page, but it laid the groundwork for the idea that has since really taken off. The idea is if you imagine a thin beam or a thin plate, and we have a bending wave coming in at an incident direction, if we taper the thickness of that plate, then the properties are going to change over space. So if we start at some incident position, x sub I, and we go towards the origin, and it's tapered according to some profile, we can say that the transit time of this bending wave from the incident position to the origin is going to be related to 1 over the group speed. And that itself is proportional to the square root of the thickness, which is to say that as the thickness decreases, the speed of the wave also decreases. So it gets slower as it moves along. So we can calculate this. It's going to vary over space. So we take a spatial integral. In particular, it might not be obvious, but in particular, if we have a quadratic power law, then in theory, as the thickness goes to 0 at the origin, the transit time, the time it takes to go from x sub I to the origin, goes to infinity. So it increases indefinitely. Similarly, we can, using some geometric approximations, define the reflection coefficient as e raised to the power of the negative frequency times eta, which is the loss factor of the material, times this transit time. And so you'll see that as the transit time goes to infinity, the reflection coefficient goes to 0. And so this is the idea of an acoustic black hole in the ideal case. Now, of course, if we have some non-zero truncation thickness at the end, then our reflection coefficient is going to be greater than 0. And in fact, in such materials like many metals that are actually used in practice, where the loss factor is relatively low, oftentimes the reflection coefficient is going to be very nearly 1. And so this acoustic black hole effect seems to be spoiled. It seems that we can't get this acoustic black hole effect that we want. However, we can use 2 additional properties of thin plates or thin beams, which is that the wavelength is going to be proportional to the square root of the thickness, and the amplitude, if we conserve energy going through the material, the amplitude is going to be inversely proportional to the thickness. And so what this leads to then is we see, in terms of wavelength, we see a bunching up of the wave energy because the wavelength gets much smaller. And we also see an increased displacement amplitude. And so what this means is that we are concentrating, we are localizing the displacement energy and the the strain energy into a particular region. And so this means that we can then concentrate our damping efforts in that region. And in practice, this is how acoustic black holes are implemented in real life. So here's from a recent publication in the Journal of Sound and Vibration. This is a figure of publications by year. And you can see first in 1988, the original paper by Mironov, and then it was very dormant for a long time. And then it kind of took off around, say, 2007, 2008 into 2014. And it has since really taken off in the field. Lots of research being published. I probably get notifications of new publications multiple times a month, at least once a month. And it's really taken off. In terms of what I'm calling research hubs here, there are many more researchers than I'm going to list here. But for the sake of brevity, I'm going to point out some of the more prolific authors and some of the labs that are have many more team members, but just know that there are many more researchers than I'm going to list here. Mikhail Mironov still publishes and presents at conferences, and he's in Moscow. Viktor Krylov, who actually worked with Mironov and then moved to the UK. He and Dan O'Boy are in the UK. Francois Gautier and Adrien Pellat are at Le Mans University in France. And they, in particular, have a rather large team researching acoustic black holes. There is Steve Conlon here at Penn State, who has had numerous students who have looked at the acoustic black hole effect. And then there's Li Cheng in Hong Kong, who has, again, a rather large team of students in his lab looking into different aspects of acoustic black hole design. And then a couple others. There's Jordan Cheer, who is actually my old advisor in Southampton. He's recently looked at acoustic black holes, specifically active noise control being applied to acoustic black holes, or active control, active structural control. And then there's Wonju Jeon in Korea, who is, as far as I know, the only person who is considering a particular implementation of ABH that no one else is looking at right now. As I mentioned, I sadly have to cannot include anyone, or can't include everyone, and so I have to omit some people. There is a small group in Spain. There are several small groups in China, especially in Nanjing, and there's also another group in Indiana in the United States at Purdue University, who are looking into this as well. But these are kind of the main players, if you will. There are many different ways that acoustic black holes can be implemented in practice, because again, the only prescription is on the thickness profile. And so here are just a couple examples. In practice, the most common are going to be these two, A and D. And so we will call these at the top, it's going to be a one-dimensional or 1D ABH, and then the lower one is a two-dimensional or 2D ABH. So now I'm going to review a little bit of historical and current research into acoustic black holes. Again, looking at this, this figure with publication history, I'm going to go in roughly chronological order, but not exactly. I'm going to jump around a little bit as we get closer to modern day. So this is just looking at reflection from an imperfect ABH. Viktor Krylov in the UK was the first to suggest, hey, well, we have this bunching up of strain energy. And so let's, even though the acoustic black hole is not perfect in practice, we can still get much of the benefits from it by adding a damping layer at the end. And so the figure on your left is the solid line represents the reflection coefficient if there were no damping layer. And you can see it is very nearly 1. The dashed dot line is the geometric approximation when we do add Krylov used to determine the reflection coefficient. And you can see that it follows the same general trend as the dashed line follows the same general trend as the geometric approximation, but it has these noticeable dips, these noticeable minima. Some of the first experiments were also conducted by Viktor Krylov in the UK. Here's just an example. It's a little bit difficult to read the plot, but I think it's the solid line is without an ABH, so it's just a uniform plate, and the dashed line is with the ABH taper at the end. And you can see that there is a noticeable reduction, especially above, say, 3,500 Hertz. There's a noticeable reduction in the amount of vibration. Going over now to France at the team in Le Mans. On your left, this is a look at the essentially the modal loss factor of different modes of a one-dimensional ABH. All you need to concern yourself with is the rings. The green rings correspond to a perfectly uniform, unmodified beam, and then the solid circles correspond to a beam with an ABH taper at the end. And as we move away from the 90-degree angle, that means an increased modal loss factor. So you'll notice that in general, we do have an overall increase in the modal loss factor, but in particular, we have a few discrete modes that have a much increased modal loss factor. Now on your right, we see the modal overlap factor. So this is going to correspond to modal density as well as the modal loss factor. And you can see that similarly to the other plot, we have a much increased modal density, a much increased modal overlap factor when we include an ABH. And this makes a lot of sense if we consider the bunching up of the wavelengths. We can kind of fit more in there. And so we have an increased number of modes for a given frequency bandwidth. Still at Le Mans, but a little bit more recently, this is from a paper that was published last year. They looked at the ABH effect in terms of what they call critical coupling. So if we use an impedance matrix method for the analysis, and so we think of it in terms of a number of discrete uniform beam segments, but going down in thickness, we can calculate what frequencies, what complex frequencies result in poles and zeros. So what result in singularities and zeros. And they looked at the ABH effect as modulating these poles and zeros in the complex phase plane. And in particular, again, because we have the increase in modal density, we have more zeros closer together for a given bandwidth. And designing the ABH correctly and then the damping layer correctly, we can modulate it so that those zeros line up with the real axis, which corresponds to trapped modes or this critical coupling condition. A group, so this is Li Cheng, I believe, in Hong Kong, and they looked at if we go to very high frequencies, we can actually use the geometric approach to analyze the acoustic black hole effect in terms of a lensing. And so if we trace some ray trajectories, we can see that depending on the exact design of the ABH, we get this focusing to a certain point within the two-dimensional ABH. And actually, this has also been used as almost a lens to refract acoustic energy. Here at Penn State, Steve Conlon and his team have looked at acoustic black holes for increasing sound transmission loss. So on your left, you have a picture of the speaker, or a picture of the plate with a number of ABH indentations on it. In the center, it's a wave number transform. And so what that shows basically is that it spreads the energy out into different wavelengths or different wave numbers. So rather than be concentrated around this black ring, it's spread out into a wider area out towards the white circle. And what that means is that less sound is effectively radiated. You can think about this in terms of, for effective radiation of sound in a beam or plate, we want supersonic wave speeds. But if we slow the wave speed down in the ABH feature, then we can reach subsonic wave speeds, and therefore we have this decoupling effect is what they call it. And then on your right, we have radiation efficiencies that they calculated, or that they measured rather, for a number of different configurations. As I mentioned, these acoustic black holes can be used as almost lenses. And so this pushes them into the realm of metamaterials when you have arrays of them. I'm not going to go through each of these, but just know that several different authors, such as Semperlotti at Purdue University, Fabio Semperlotti, and Li Chang, and a number of others I'm sure I'm forgetting, have looked at arrays of acoustic black holes as effective structural metamaterials. In terms of applications, acoustic black holes have not seen widespread application to date for a number of reasons, probably the most important being manufacturing is not viable on a large scale. But certain authors have looked at the application of acoustic black holes to turbine blades, or on the bottom here, we have an engine cover, one without and one with two-dimensional ABH features. So there are many applications that could be envisioned for acoustic black holes, but as of yet, we've not seen widespread adoption in any particular application. Okay. So with that background out of the way, I'm going to now move on to my own research. I'm going to present a optimization study that I performed. Going back to, once again, this will be the last time I promise, going back to this figure, I just want to explain some of the motivation behind my research. So I started my PhD in 2016. As Fernando mentioned, we took the qualifying exam together in 2017. And so just to give you a reference of where I land on this chart. So we see that this is as of the end of 2019, beginning of 2020. There were 101 published journal articles regarding acoustic black holes. Of those 101 articles, only 3 involve any kind of formal optimization of ABH design. And that means, and one of those came before I started my PhD work. One of those came out of my PhD work, and then another was published separately by a different team while I was still doing my thesis work. And this means that historically, there hasn't been a clear understanding of what constitutes optimal ABH design, especially in more practical settings, so finite settings, rather than considering an ABH termination attached to like an infinite structure. What happens when we apply that ABH into a finite practical structure? And historically, there hasn't been a lot of work into the optimal design. And so the idea is that by applying some formal optimization to different applications and analyzing the results and the trends and the trade-offs, we can gain insight into the inherent trade-offs in the design in a more holistic way than previous authors have addressed. In particular, this study is going to address the question of to what extent is modeling the second dimension, the thickness dimension, important? So just a little bit of background. As I mentioned, acoustic black hole theory, the original theory, only prescribes the thickness variation, but not any kind of distribution, especially about what I'm calling the central plane or the mid plane of the beam or the plate. And most often, in one-dimensional analyses, it's assumed that it's going to be symmetric about the central plane. And so this is an assumption that's baked into things like the Euler-Bernoulli beam equation, and often baked into analyses of other authors like impedance matrix methods and such. However, for manufacturing reasons, as you saw in many of the pictures, ABHs are usually manufactured by taking a uniform structure and then removing material in one direction. And so this means that then the thickness distribution is going to be asymmetric or non-symmetric about that central plane. It's going to be focused towards one side or the other. And so in 1D analysis, it's rare to mention which of these two styles is being included in the model, is being analyzed. And while at low frequencies, they will be more or less equivalent, at higher frequencies, they're not going to be. They'll have different dynamics. In addition, as a third style, we included what we're calling a double leaf style. And this was proposed by Krylov and Zhou et al. And actually, we saw a picture of it on the Metamaterials slide. And I'll show you a picture in, I think, the next slide or the next few slides. So here are the three styles we're considering. What we're calling the standard symmetric style, the standard non-symmetric style, and then this double leaf style. And you can imagine the double leaf style as the first one, the symmetric style, being split in half, rotated, and then pasted back together again. And just for reference, each of these colors, purple, pink, and orange, will be used throughout the slides to refer to each of the three styles, just so that you can understand the plots a little bit better, a little bit easier visually. The problem, the optimization problem that we're addressing here, is a one-dimensional ABH vibration absorber embedded in a simply supported plate. It's one-dimensional because even though we're going to be modeling explicitly 2 dimensions, it's called one-dimensional because the thickness variation only varies in 1 dimension. It's going to be excited by harmonic point force. The taper shape is going to follow this power law taper. So you'll notice that it's x not raised to the power of 2. It's not quadratic, but it's raised to an arbitrary power of m. And it turns out that the same theory that results in this 0 reflection from before also works for powers of 2 or higher. So we're going to have this taper profile that it's going to be restricted to follow. It'll have some non-zero truncation thickness. Otherwise, it's going to be a continuously varying thickness profile. In addition, we'll also vary the position, so where the ABH is, where it lands along the beam or along the plate, and we'll also be varying the amount of added damping. We'll have 2 objectives. The first is going to be minimizing the overall mass, and the second is a bit complex, but we are going to be recording the velocity response and then averaging it over the entire length of the structure, and we'll want to minimize that. So I'll just refer to that as the vibration response. So we want to minimize mass and we want to minimize the vibration response. Here's a graphic illustration of the problem, and our design variables will have 5. The first will be the length of the ABH. The second will be the minimum thickness, the truncation thickness. The third will be that power law power. The fourth will be the position, and the fifth will be the percent of the ABH that has damping applied to it. Here, just mathematically, are our 2 objectives. The first one is the overall mass. The second one, again, we're calculating the velocity response, and we're going to average that over the entire length. And then we'll also evaluate that in some bandwidth and then take an overall average at that. We'll integrate across frequency. In terms of constraints, the dynamics will need to satisfy plane strain elastodynamic equations. The possible designs will be limited by the upper and lower values of each of the 5 parameters. And then the end boundary conditions for the plate will be pinned boundary conditions. Our numerical model looks as such, so we'll have a multi-objective evolutionary algorithm as our optimizer. And then for the finite element analysis, we'll be using Nastran. So we need some way to connect these two. And for that, I wrote a number of bespoke scripts in MATLAB and functions in MATLAB. And it works by first, our optimizer will pass the 5 design variables to the MATLAB functions. It will take them in, process them, and then write out analysis files that can be read into Nastran. Nastran will perform the analysis and then pass nodal displacements to our MATLAB functions, which will then post-process the results and give the 2 objective values to our optimizer. I'm going to spend a little bit of time talking through this slide. These are the results for the symmetric style. The solid purple curve that you see is what is called the Pareto front, and it corresponds to the trade-off between the 2 objectives. So this is your no free lunch zone. The yellow circles correspond to just example designs and where they land in the objective space. So it gives a picture of the overall shape of the objective space. The black X there is for a completely uniform, unmodified beam. And you'll see that the 2 objectives are normalized. So it lands at 1, 1 for both objectives. And then the plus sign there is the same uniform beam, but it has damping added to it. And so you'll see that actually, notably, we don't reach this Pareto front. We don't reach this trade-off between the 2 objectives until we reduce the mass by a certain amount. So that's to say that from our unmodified beam, we can design an ABH such that we lower mass and lower the vibration response. And there's not a trade-off between the 2 objectives. And so this is remarkable that we don't have this trade-off right off the bat. We have a region where we can improve both objectives before we have to give up something to gain in another area. Here is the same plot for the non-symmetric style. And you'll see that overall, the shape of the objective space is similar, but it's different. Similarly, for the double leaf style, we have a similar objective space, but again, it's going to be unique. And just to compare the 3 together here, you'll notice that the pink curve, the non-symmetric style, makes a better use of the mass. So for a given amount of mass overall, it is able to lower the vibration response greater than the other 2 styles, which is significant here. You'll see that then in second is the double leaf style, and in third is the symmetric style. We can take each of these Pareto fronts and stretch them out, and then plot each of the design variables, each of the 5 design variables, according to that Pareto front, and see the trends in the design parameters. So you'll notice that there's not a lot of variation in the length or the minimum thickness. There's some variation in the taper power. There's some ambiguity, especially at the upper range, where we're minimizing the response, but we are maximizing mass or increasing mass. And then also in the position, there's some wiggle room there. What's noticeable is that there's a strong dependence on the amount of damping. So what I've plotted here instead of the percent damping is the absolute length of the damping that's being applied. You can see that it's very nearly a line, a linear dependence. So we see that in addition to optimal ABH design, it's critical to properly design your damping being applied to the ABH. We can now look at what I'm calling these threshold designs. It's the threshold of the Pareto front, and we can look at some of the properties of those 3 designs compared to one another. So for example, here's the squared, spatially average squared velocity spectra. So this is just our second objective, but rather than integrating over frequency, we're evaluating it at as a function of frequency. And so for reference, we have the uniform beam with added damping as a dashed black curve here. And you can see that in all three cases, we have a greatly increased number of peaks. And this again goes back to our idea of an increased modal density by including an ABH feature. And although it's on a logarithmic scale, it's a little bit hard to see. It's significant that even though we have this increased number of peaks in the spectra, the average value is remarkably lower than it is for the uniform beam, even with damping. Another thing to note is if we look at the pink curve again, the non-symmetric style, we see that there is much less vibration, much less velocity response compared to the other two spectra, and that plays out in our objective value and our Pareto front that we saw before. And then also for the double leaf style in orange, we see, obviously we see an increase in modal density, but it's even greater for the double leaf style compared to the other two styles. And this corresponds to results that have been reported in the literature where each of the two halves, each of the two leaves acts as an ABH independent of one another in a sense. And so because they are half the thickness of, say, the symmetric style, because we're cutting it in half, flipping it, and pasting it back together, they're going to be half the thickness. And so we'll have an increase, a further increase in the modal density. We can also look at, although this was not included in the optimization problem, we can also look at radiated sound. So this was calculated for far field radiation using the Rayleigh integral. And this is more effectively a radiation per unit width because we're only looking at a two-dimensional slice of like an infinite plate. So this is radiated sound power per unit width. Again, the colors correspond to each of the three styles, and the black bars correspond to an unmodified uniform beam with damping added. And you'll see that all of the three ABH styles outperform the unmodified beam, even with damping, in terms of decreasing the amount of radiated sound power. Now, compared to one another, the three styles, the symmetric style is absolutely less effective at reducing the amount of radiated sound compared to the other two styles, which perform comparably to one another. So the non-symmetric and the double leaf styles perform comparably for reducing radiated sound power, then the symmetric style, and then last is the unmodified beam, as we expect. So coming back to our original question, how important is it to explicitly model the second dimension? Well, it turns out that it's absolutely critical because all of the variations we see are due, in the results here, are due to the choice of style, right? So some of the key takeaways from this study, first of all, it was the first, at the time it was published, it was the first to directly compare these three styles, which are common in the literature. And there's a citation in case you want to go find it. It showed that modeling the second dimension is critical for accurately modeling the ABH effect. And while the precise choice of which is best might depend on other external goals, the non-symmetric style seems to be the preferred style of the three for vibration reduction. It also showed, and this was not expected at the outset, but it also showed that the damping design can be critical for effective ABH performance. And it's noteworthy, it's should be noted that following the presentation of these results, multiple studies came out afterwards explicitly looking into the design of the damping application to the ABH. Okay, so I'm just going to finish up now with a few concluding remarks. In summary, we saw that the so-called acoustic black hole effect, it really has, in this context, nothing to do with in-air acoustics. But the acoustic black hole effect, as it's come to be known, is produced by tailoring the thickness of a beam or a plate using a power law profile with a power of 2 or greater. What this does is it creates an area of smaller wavelength and larger amplitude, which localizes the strain energy so that we can more effectively concentrate our damping efforts in a smaller area. And additionally, for radiated sound, it results in a slower wave speed, which produces this acoustic decoupling effect, so that ABHs compared to unmodified structures are relatively poor radiators of sound. There is a great amount of flexibility of variation in how an acoustic black hole feature is implemented in practice. But as we saw from the optimization results, how it is implemented matters greatly. And we also saw that the particular design of the damping layout is a very important factor as well. And so these two should go hand in hand. As just, I'm calling this an epilogue, something to finish off with, it should be noted that very similar analysis to what we saw with bending waves in a thin beam or a thin plate, going to 0 wave speed, not being reflected back. Similar calculations can be carried out for in-air calculations in one dimension. And how the analysis works is by using the Webster-Horn equation and including wall impedances, a term for wall impedances. You can get the same effect using, again, a power law, although it will also work for linear laws. So it doesn't have to be a power of 2 or greater, it can be a power of 1 or greater. And you can get, in theory, the exact same effect. And so this has been an area that's been historically relatively untapped. There have been a few exploratory investigations. I've seen one paper that looked at muffler design using what are called sonic black holes to differentiate them from acoustic black holes. But this diagram comes from a paper that was published very recently by the team out of Hong Kong into sonic black holes. And they themselves mentioned that there has not been a lot of research done to date on this use of the power law profile. So if anyone is looking to get into this field, obviously there's still a lot more that can be done with acoustic black holes in structures, but I would think it would also be very profitable, very valuable to research the in-air possibilities of these sonic black holes. And with that, I will thank you for having me, and I'd be happy to answer any questions that you might have. Hi, Fernando, I see you're raising your hand.
Yeah, Cameron, well, fantastic presentation. Thank you very much.
Thank you.
Also, thank you for TJ for, I listened to the presentation in the Spanish channel and it sounded very well.
Good, good.
Cameron, I do have 2 questions actually. One is, I think I see an enormous potential with this technique to sort of mitigate vibrations in buildings, in structures in buildings, just the foundations and also the slabs and the beams could be so shaping those structures using acoustic black holes could potentially improve vibration isolation from this kind of structures. That has been explored before. What are you?
My understanding is that hasn't been explored, certainly not in the literature. Hasn't been explored to date, but it would be interesting. It is worth noting that obviously we're removing material to get this effect. And so that will ultimately weaken the structure. And so sometimes especially in the foundation of a building, that might be undesired, but there are ways, like with the double leaf style, there are ways to get some of that strength back. And so that might be an interesting application for that double leaf style.
I guess that Jonathan Broyles did some research on that recently, I think.
Yes, he did look at structural optimization of concrete slabs. I'm not sure that I remember there being acoustic black hole features in there explicitly.
Probably not.
But well, it's quite possible because he's been working with my advisor, Dr. Shepard, Dr. Micah Shepard, on some of the optimization work, and so it's quite possible that they've looked at that and just not published any results yet.
Okay, and the other question I have is, all this analysis has been done using finite elements, so it's a numerical analysis. Have you implemented some of this in actual structures, test structures, or did you do some of that as well?
I did not. All of my work was on the computational side. As I mentioned, I've worked with Dr. Micah Shepard, who is also at Penn State, and he and Steve Conlin work closely together. And so they have other students doing experimental work in acoustic black holes.
Okay, so we have a question from the audience, 2 questions actually, from Arturo. Do you know any practical application of acoustic black holes already implemented? That is his question.
Yeah, no, that's a great question. To my knowledge, application is not widespread. We saw the engine cover there, which if you noticed had a Mercedes logo. They have looked into this. I don't have enough information to know if it's currently in practice or if it's going to be in future models, or if they prototyped it and decided it was not worth it. So as of now, there is not widespread application out there in the world.
So thank you for that. We have another question from Jose Palazuelos. What do you think is the earlier? What do you think is the earlier to apply or easiest application of acoustic black holes? The earlier to apply or easiest applications?
Okay, what's the easiest application? It's going to depend on what kind of problem you're tackling. I would say that we saw that this acoustic decoupling effect comes from including acoustic black holes in panels. And certainly that is a relatively easy thing. It's not super easy to manufacture right now on a large scale, but it's easy to implement as partitions between, say, 2 rooms, for example. And it does reduce or it increases the transmission loss to a significant degree. So I would say that would be the easiest to implement.
Well, Jose said thank you.
You're very welcome. Thank you for great questions.
Yeah, sure. Let's see if someone else types something in.
I also mentioned with Fernando that I would be interested in distributing these slides. So we'll figure out a way to get that to the group, to the chapter, because I've made a point of including a number of references in these slides. So you can, if you want to go and read more, there's a lot out there, and hopefully this will help.
It's very generous on your side, Cameron. Thank you. Thank you very much. We still have another question from Hector Garcia. I suspect he's Hector Garcia Majan. I would like to know a bit more about the computing power to get results.
Oh, that's so I'm going to take that as meaning the computer hardware and software to get the results. So these were run on a cluster of computers. It was run on a single node of, I think it's 48 processors. So we're talking about high-powered computing, HPC here, and Nastran was run in parallel for these calculations. I don't recall off the top of my head the exact models, unfortunately, of the processors, but it was run as a distributed model across multiple processors.
There is another question from Jose Palazuelos. Best way to keep up to date with this matter?
That's a brilliant question. How I do it is I have alerts set from Google Scholar. And if you just have acoustic black hole or acoustic black hole effect, it used to be that some authors would, or that search term would not capture all of them. And so you'd have to use a few other ones like power law taper or something. I think right now, if you just have search terms for acoustic black hole and or acoustic black hole effect, that will capture almost all of it. And you'll get an email whenever something comes up. As I mentioned at the beginning, this will also capture some of the physics papers about this analog black hole, but you can just filter through those manually. It's not a large number.
Let's see, we have another question. Well, doesn't look like. Well, I would like to thank once again Cameron for this great presentation. So in the chapter, we're constantly struggling to move a little bit away from architectural acoustics, which dominates our presentations and events. So this is very, very, very interesting for our chapter and our sort of promotion of different branches of acoustics, and this computational stuff is really, really interesting for what we're doing. So thank you very much. I'm sure that many people that perhaps weren't aware of this now have a broader interest in this optimization schemes and stuff you've explained so well.
Well, thank you.
Thank you
I
very much.
hope so.